So within the scope for today's session, we're going to focus on the recent innovations that we've made in downhole video and two of the main technology ingredients that are involved in that innovation. Firstly, we'll take a look at the concept of visual analytics and introduce that, along with the deliverables that we can produce and some of the data science that sits behind it. In addition, we'll also look at one of the new data acquisition technologies we've built around this framework, a system that we call OPTIS Infinity, and that's a key part of the overall system, and we use that to acquire the source data ready to analyze and process with these visual analytics techniques. We'll take some time to explore what's possible through this application of these technologies, and we'll demonstrate how the two elements have combined to help transform the way we can now use downhole video and support that with some case studies from real scopes of work that we've performed around the world. So with that, what is visual analytics? Well, put simply, it means quantified vision. And by mapping the way the overall optical system manipulates the captured rays of light, we've been able to calculate a transform function that helps restore the true geometry of any object that we have within the field of view. This enables us to make highly accurate measurements of the features that we're seeing and any anomalies in the well in real time at the well site. So to understand not only the root cause, but also the severity of the issue at hand. And with this knowledge, we can help improve decision making and hopefully make the action that you take more decisive. So there are two examples in this little video clip. The first one, looking down at a set of hydrates, as you can see now. And this is using our down view camera. And we could take spot measurements of length, distance, proximity to the sidewall. And from that, we can help understand how big they are. And if this was something more severe, potentially how we'd actually remove it and select the right tool for the job. The second example, we're now looking sideways at the pipe wall and looking at some micro corrosion events that have occurred on this well. A little bit of a surprise for the operator, and that's why we took some time to try and quantify them. But as you can see, we can draw freehand, we can do point-to-point measurements, we can calculate linear distances, cross-sectional areas, and the best thing about this is that we can come back over time and monitor the progress or rate of change of these anomalies. So in this case, we can help understand if the corrosion inhibition program that was put in place has been effective and possibly give some extra information on life of well calculations and overall life of well management. As we mentioned, the visual analytics processes are supported by a number of technologies, and one of them is OPTIS Infinity. This is the culmination of several years of dedicated research, development, and engineering effort to deliver the world's first array side view camera for downhole applications. This technology features 4 azimuthally aligned video cameras recording EV's trademark high resolution and high frame rate video, with 4 cameras mounted at the same depth plane, looking at 90 degrees to each other. This groundbreaking innovation has a full 360-degree view of the well and enables us to create a vivid and dynamic map of well conditions from the lubricator all the way down to the toe in a continuous run-in hole. We use it very much like a logging tool rather than a static point measurement. This unique sensor configuration is also coupled and supported with advanced image processing techniques, in which the 4 concurrent video feeds are then combined and analyzed in a process that we know as mosaicing. And this mosaic will create a single continuous 360-degree image that's approximately 3,000 pixels wide, and in theory, we can make it infinitely long. We also have an integrated down view camera that you can have as an option, so you get the best possible field of view and the most complete perspective of downhole conditions. And here you can see not only the 4 cameras, but also the patented lens configuration that we've placed around them, and the twin LED arrays top and bottom that we use to illuminate the field of view. And this technology can be used on all modes of conveyance, slickline, E-line, coiled tubing, either in real time, memory mode, or even a hybrid of the two. So pretty much all modes of conveyance, we have it covered. So just to take a look at how this system works, this is the type of view that we'd be able to deliver at the well site. The 4 concurrent video feeds placed side by side with camera 1 on the left and camera 4 on the right. And here you can see that there's an overlap in the field of view. So we're getting actually more than 360 degrees on the screen at any given time. And what we're showing on the right-hand side is the sort of thing we're able to achieve post-process. As we're playing the video, the computer system is looking for common points between adjacent camera feeds. We call these key points that it uses to compare the video. And by tracking their location and their speed as they move through the field of view, we can understand the properties of the surrounding area and the speed at which we're passing through them. The system then uses that to calculate the distance that we've traveled and then combine the 4 independent feeds to create the continuous 360-degree image that we're seeing on the right-hand side. Now, the really interesting part about that is that we don't have to rely on any measurements from surface to tell us what depth we're at and how fast we're moving. That's all calculated from the pictures downhole. So in that sense, we're able to do a true speed identification right at the BHA to understand its motion and behavior. And that in itself is a useful byproduct that we've put a patent on to help with the speed correction of other logs and other interventions that we're having to run at the same time. But just to take a little bit more detailed look at this image that we've created, if we just zoom in over one of the areas of interest. Oh, did we have a question? No, I guess not. Well, here you can see that we've zoomed in on one of the areas of interest, and this is over the actual ported area of this sliding sleeve assembly that we've been showing. And you can see the level of detail that we can capture with this video system. Not only the individual ports, but some of the marks on the inside pipe wall, and even the presence of some very light, soft solids that have accumulated on the low side of this assembly. These were identified as small bits of bacterial growth that were floating freely in some parts, but also had become settled at the low side of these ports there. I should also stress for completeness that the image you're seeing on screen has been downsampled by roughly 50%, just to make sure that it will fit onto the PowerPoint. And as well as that, I should be completely fair to the system in saying that streaming it over Microsoft Teams as we are today will probably have an effect on the quality of the image that you're seeing at your end, and also potentially some of the videos as well. But if you'd like to see some of this technology in action, a number of the video clips and images we're going to show you are available on our website, and you can see them there in their full resolution, and also without the compromise into video quality and playback. So worth taking a look once the event's over. But moving on, once we've acquired this data, we can do a number of things with it. Firstly, we can view it from any angle we like. And in this view, what we've done is we've recreated the 3-dimensional shape of the sliding sleeve from an engineering drawing, and then superimposed our 360-degree image on top of it. So now we're looking at the true geometry viewed as if it was a downward camera, but actually with data that we acquired looking sideways. And we can manipulate this view to any angle, any orientation that we like, and try and look for any changes in expected shape compared to the original plan, and try and identify if there are any anomalies or any damaged areas in there that might have occurred over time. So again, a very powerful data set. We can do anything we like in 2 or 3 dimensions to get the view that we want and take a very detailed look at the area of interest. And we can take that even a step further. In this view, we're seeing the combination of our 360-degree image, depth matched with multi-finger caliper data from the same well. This was actually conducted on 2 separate runs, but we could run them simultaneously to get this complete data set in one run-in hole. But the great thing about it is that we get quantified information about the radial position and overall shape of the completion from the multi-finger caliper. But we get a lot more information about the overall texture, the composition, and small features and details from the video image as well. So a terrific blend there of quantitative and high resolution image. The object on the right-hand side is a hybrid of the 2 data sets. We're actually using the 3-dimensional model created by the multi-finger caliper data, and again, superimposing our image on top of that. So now we have a dynamic object that we can view again from any angle and manipulate any way we like, and even take detailed views from any angle. And all of these tools are available in a combined analysis suite that we provide, and the end user, the customer at the end of the job, would receive a copy of this and can interact with the data in any way that they wish. But for a log analyst or a petrophysicist looking at this data, it's so useful to have not only the log data, but also the image, because a lot of the questions that you may have about what's really going on in the well can be answered by the combination of the two, where you might be missing that information just looking one in isolation. So just to move the story forward, there are a number of different challenges that we can use this technology in combination to good effect. And what we're showing on screen is a sample of 8 challenges that EV are actively involved with helping well operators to overcome issues that they may be experiencing. On the top of this video wall, we have what you might consider to be more proactive evaluation services, helping with long-term well management, either integrity or well performance, including corrosion VA, which is helping to understand the integrity of structures and support the extension of life of wells. Then we have sand VA, evaluating the performance and condition of sand control systems and helping to identify any source of sand inflow. Then perforation VA, a technique that has been widely adopted in the unconventional hydraulic fracturing market in North America. And this is being used to help optimize frac design and completion design to optimize hydraulic fracturing practices. And we'll see a little bit more about both of these 2 techniques in case studies in a few moments' time. We can also help identify the source and inflow of water using water VA, something that may complement a production log and reveal the exact location where you have water breakthrough. Again, helping to isolate its source and maximize hydrocarbon recovery. Then on the second line, what you might consider to be more reactive diagnostic services to assist with immediate remediation. These might include the identification of leak sites and helping to understand what's caused them and what the surrounding area looks like to determine what course of remediation to take. We also do a large amount of work in understanding wellbore restrictions, not just straightforward obstructions or collapse like we see here, but even pipe deformation that we can then use multi-finger caliper combined with video to understand the limits of well entry to help you meet your objectives without compromising the job. We also provide real-time fishing support, understanding the object that's been dropped in the well or is blocking access, and helping to remove that safely and efficiently. And finally, looking at more complex items, completion components, maybe elements that have a motion or active ingredient to them, such as valves or extension joints, sliding sleeves, anything that has motion associated with it, and you might rely on it working actively in some form. And by using the high resolution, high frame rate video, we can understand their behavior and hopefully help you get them back on track if they are causing any problems. So again, in this session, we can't go through all of these case studies. So what we're going to take a look at is how we've used perforation VA with great success in North America, And then we'll extend that into a sort of logical next sequence, looking at sand control systems and how we can help diagnose and evaluate their performance. So let's start with perforation VA. And overall, the industry challenged with hydraulic fracturing of wells. And just to be clear, in these examples, we're going to be talking about plug and perf operations, not necessarily completions with sliding sleeves and frac sleeves. But the whole premise of hydraulic fracturing is to create pathways that connect the well to the reservoir. Put simply, if you do not fracture these wells, they just will not flow. And I'm probably preaching to the choir here. You'll notice with much more detail than I do. But the objective is to get nice, evenly distributed fractures all the way along the length of the well, trying to maximize the contact between the well and the reservoir. And that way, we'll have the maximum level of production, long-term recovery, and also reducing the risk of a well integrity or well conformance event by trying to avoid breaking through to a neighboring well. But a big part of the challenge is about managing cost, and whether it's just the raw materials or the combination of that with the horsepower required. Fracking the well is a big part of the well delivery cost, in some cases 40% or upwards. So ensuring that every dollar that you spend on this item is used effectively and efficiently is a big part of getting return on investment where you want it to be. And initial design work and execution of that first frac could help minimize future costs and increase productivity, possibly deferring future interventions and maybe even deferring refracs and restimulation work over time. And of course, if we get it right, we can maximize recovery. And if we compare, a typical unconventional well with maybe a 8 to 12% total recovery rate to a conventional well with 25 to 50% recovery, small incremental gains in production from an unconventional well will have a big impact on the cost-effective nature of that installation. And if we look at that up until recent events, if we consider that in just the US alone, the number of wells predicted to be drilled and then fractured is somewhere in the 10 to 20,000 region per annum, this is a massive industry challenge, and with great value if we can optimize this and improve it in some way. So I'm not going to go into this in a huge amount of detail. We actually covered a lot of the subject matter on this challenge in a previous webinar, and we'd be delighted to share information on that or even arrange a rerun. But what I will do is just go through the basics of the analysis sequence and then a few of the key trends that we observe as a result of this analysis. So again, let's start with the video feed, the 360-degree view of the well that we take whilst we're acquiring data. And as we go through, the analyst will pick each individual perforation and load it into the analysis suite. That suite will then automatically detect the perforation and the reference arm that we use to help calibrate the image and turn that into a dimensioned measurement. And as you can see here, it's a very quick process. It's heavily automated with minimum intervention required from the analyst. So that perforation in its entirety took probably a minute or so to capture from the video and then to analyze. And once the analyst is happy with the way that perforation has been picked, if they're not, they might be able to tweak the boundaries and the selection criteria there. But once everything's satisfactory, they can then move on with the image calibration and convert that into dimensions. And all of the information about the geometry of that perforation is then stored into a data set for further analysis. And in that data set, we can look at things like the diameter, area, perimeter, and key to that as well, also the azimuthal position around the circumference of the pipe. So again, just concentrating on two of the main trends that we can see here, we're going to talk about two biases that we can help try and overcome or at least manage. And the first of these is the azimuthal bias. This is the preference for larger holes to be created on the low side of the pipe. And you can see here on this first image that we have, this is an average across all of the stages in a single well. And in this one example, the cross-sectional area after treatment is 300 times, 300% greater than it is on the high side of the well. And we have a variation there in between. So what this indicates to us is that we have a potential overstimulation in one orientation and perhaps understimulation in another. And if we think back to our original premise of even distribution of fractures and then proppant placement around the wellbore, then we're certainly falling a little bit short of that on this one particular example. And this well isn't alone in that. If we then take a slightly more holistic view, the charts we're going to plot on the right-hand side show the overall diameter in inches of a data set that contains over 20,000 data points, over 20,000 different perforations we've captured and analyzed. And again, we're going to plot those against the azimuth, this time linearly along the horizontal axis, with 180 degrees being the low side of the well. And what we see here is actually a classic bell shape or Gaussian shaped curve, showing that there is a tendency for smaller holes at the high side of the well, and then larger holes on the low side. This trend is somewhat exaggerated during the fracturing process. As we pump proppant through the perforations, they will enlarge. That is the technique that we use to measure the effectiveness of that proppant placement. And what we see is that what starts as a big hole has a lower resistance than a smaller hole. So they will then have a preference to accept the treatment compared to the smaller holes on the high side. And that, combined with gravitational effects and a preference for the slurry to flow along the lower side of the well, has a sort of compound effect, meaning that this trend is exaggerated and the gap here starts to grow and extend at the low side of the well. So again, there could be many factors driving this, and what we can help with the data that we can acquire is potentially choosing a perforation strategy and orientation that minimizes the overstimulation and understimulation conundrum that we're seeing here. The next trend that we see as a common effect is what we call the heel-toe bias. And if we consider each stage and the placement of proppant along that stage, in this case, axially along the well path, we have a situation where we may have a tendency to overstimulate at the heel and not get enough treatment into the toe. So first up, we're going to take a look at this effect with the geometrically designed stages. In these cases, each stage is treated as equal, and the number of perforations is uniform across each cluster within the stage. And what we're looking for is a 50-50 distribution of proppant between the toe and the heel. But if we overlay the results from close to 300 different stages that we've analyzed, we can see that other than one or two stages where there's 2 or 3 clusters per stage, anything above that, there is a dominance for proppant placement to be stronger at the heel than it is at the toe, which is indicated by the larger blue bar compared to the gray bar alongside. So what can we do about this? Well, the good news is that we can, through iterative design process, actually engineer this process out. And with a little bit of experimentation, we can achieve that 50-50 bias that we're looking for. And to demonstrate that and how it can be controlled, we're going to take a look at one of the engineering criteria that we can adjust. And in this case, we're going to look at stages with 10 clusters. And I really want to be clear here that this isn't a cookie cutter approach that one size will fit all. This is pretty much unique to each individual well and potentially field. So the numbers that we present here are just unique to the data set that we looked at. But the variable we're going to discuss is increasing the number of perforations in the toe of the stage compared to the heel. By effectively creating a larger flowing area towards the toe, we're trying to encourage fluids to move down there and to try and dissipate and distribute the pressures more evenly across the stage to get a more even distribution of treatment. But if we look at the first data point, where we've placed nearly 30 to 40% extra perforations in the toe, we can actually see that we can reverse the heel trend. We now actually have a toe bias. We've over-engineered the result, and we've got more proppant being placed at the toe of the stage than we had at the heel. Then as we come down the level of increased perforations, you can see that trend is starting to drop. And as we come towards the 10 to 20% extra, we're getting towards that 50-50 neutral position. And in this case, it happened to be that simply adding somewhere between 1 and 10% extra perforations at the toe delivered that optimal 50-50 bias. Or in fact, you should say the lack of bias. And then if we look at adding 0 holes, well, that's really going back to the geometric design. And the results are very consistent. Somewhere around a 54% heel bias here, compared to an overall 58% bias that we observed in nearly 300 geometric stages. So again, this is just one of the parameters that could be varied. But the key thing here, whether it's the heel toe bias or whether it's the azimuthal bias, the technique that we use here, perforation VA, gives us the tool to analyze the changes and the results of changes that have been made in that engineered design. We can now understand if we've been successful in the changes that we've made, whether we've gone far enough, or perhaps in some cases, whether we've gone too far with the changes. And through that, we can help iterate the design process until we get the desired result. That can then be applied on a more field-wide basis to help deliver the optimum result on multiple wells. And that will help us achieve this goal of more even proppant placement, more even fracture distribution, and hopefully better economics and long-term recovery. So I just want to spend a little bit of time looking at the evolution of this service and really the impact of the 2 technology ingredients we added into this equation. We've been analyzing perforations for close to 5 years now overall, taking measurements and turning them into meaningful data. So you can see here, this chart dates back to the end of 2016 and right up to present day. And then we'll take a look at the number of perforations that we've analyzed on the vertical axis. On the right-hand side, we're going to look at the main KPI that we set up for this service. Firstly, the accuracy of the measurement, or in this case, the uncertainty in the measurement that we had. And the gray bar indicates our original starting point, and we'll treat that as 100%. We're then going to take a look at the turnaround time, how long it takes to deliver an answer based on the analysis that we're making, because that has a certain effect as well, that we need it to be timely enough to influence potentially the next well and the next series of wells. And last of all, we'll take a look at the acquisition time, how long we were in the field, and in particular, any extra delay or latency that it took before putting this well onto production. So as you can see, we introduced visual analytics towards the middle part of 2017. And the result of that was that we brought down the measurement uncertainty and the processing turnaround time significantly. By integrating all of the steps that we now use in the analysis sequence, the capturing and distillation of the videos, the calibration of the image, and the conversion into a measurement, rather than doing that in separate applications and moving files around, it's all contained within the same analysis suite, and it has a lot of automation in there to make it a lot more time efficient. But also, in terms of the measurement uncertainty, we spent a lot of work and time and effort on understanding the way our optics behaved. And you can remember at the start of the presentation, we talked about understanding the way the light is distorted and creating that transform to restore the real geometry. Well, that was a big part of this, and it meant that the accuracy of the information we were capturing was significantly improved as a result. The next piece of the story was introducing OPTIS Infinity. So rather than having to use a rotating side view camera that you had to position exactly on depth, rotate it to the right location, capture the image, and then move on to the next perforation, which may only be a few inches away, we're now able to go from top to toe at a continuous speed and capture the full 360 degrees continuously. That had an enormous effect on the efficiency at the well site. And what was taking us, in some cases, 3 or more days to acquire data, we are doing now in an 8 to 12 hour operation. So a massively increased efficiency there. And that's also led to us analyzing longer and longer wells and more perforations per well. So you can see here that really once we had that sweet spot of not only the analysis suite, but also the step change in performance at the well site, the trajectory of our service really took off, and we started to make a big impact there. But on top of that, the introduction of OPTIS Infinity, it also had some incremental gains on the measurement uncertainty. One of the big issues we had with the rotating camera was that we'd miss perforations from time to time. And that then gave us an uncertain response in terms of the overall data set. Now that we're capturing that full 360 view, there are very few missed perforations. And if there are, it's usually due to conditions out of our control. It also meant that the analysis sequence was a little bit improved as well. So incremental gains all around. So what started out as a very manual and time-consuming process is now a relatively slick and mainstream application that we see a great deal of repeat custom from a number of people and operators in the US and Canada. So what's next for this? Having introduced the service looking at perforations, one of the next logical areas to consider was sand control systems. So here you can see the same type of video data set acquired from OPTIS Infinity from a sand screen located in a gas storage well acquired in continental Europe. And again, we can view this from any angle we like, but the key thing is we've got that full 360-degree field of view with nothing missed, and every single one of the base holes and details of the screen captured in the field of view. We can then start to analyze these and look at their condition in a holistic way, not just 1 or 2 base holes, but potentially the entire screen and multiple screens in turn. So with that, there are 2 main things that we can look for in the screen itself to help understand the condition and performance. Firstly, in a very similar way to looking at the erosion from hydraulic fracturing, any sand inflow into the well through a breach in the screen's integrity would lead to erosion and enlargement of those base holes. And this is something that's been commented on in other papers and observed using other techniques. But with the amount of information we have with the video, we've certainly got one of the clearest views and abilities to analyze that in detail. So in this section, what we're looking at is a comparison between the expected engineering dimensions from the manufacturer in terms of diameter, perimeter, and cross-sectional area for the base holes, next to what we actually measured from the screen itself in its downhole position. The key thing on this slide is that there's very little evidence of any erosional change. The dimensions are extremely close to the expected, and to be honest, it would be hard to say that there's any pattern of erosion there whatsoever. So a very strong indication that this screen is still intact and is effective in controlling the sand. But the next thing that we can look at is more about the inflow potential through the screen. This could actually also be an injection well, so we shouldn't rule that out. But the main thing is that the screen is there to prevent the sand from coming in, but to allow the fluids to come in at the same time. So what we can do with this is start to examine the individual base holes and the voids within them to look for any anomalies and compromise to inflow capability. And if we just zoom in on one of those base holes, we can capture the expected perimeter, and we can look for the free-flowing area within it, subtract the ratio of the two, and then we can get a percentage of that base hole that may be compromised with some sort of deposition, as you can see here. And in exactly the same way as we did with the perforation analysis, we can then start to look for trends in that data. In this case, we can see a clear trend in increasing deposition and compromise to flowing area as we move down the screen from top to toe. Somewhere near the top is roughly 5% restricted area, whereas towards the toe, it's more 55% or greater. And what we were able to observe is that this was quite widespread, that of all of the base holes that we sampled, over 50% of them were compromised in some way. So it was quite a widespread problem, but clearly a trend increasing as you go towards the toe. And on top of that, we took a look at the orientation of this trend. I should say that the well was pretty much vertical, and for our orientation sensors to work, we need at least 5 degrees deviation from vertical. So there's a very strong chance that what we're showing here as being 90 degrees could actually be the low side. But again, really hard to speculate on that. So we're just plotting it from 0 through to 360, and we just assigned a quadrant to it depending on which camera we were looking at. But you can see here that there is a slight trend in one orientation. So whether it is the low side or the high side or somewhere in between, that seems to have a preference for how the solids have formed. So again, scale this up, multiple screens inside a well. Potentially this could be very useful in terms of not only looking for sand inflow and isolating it at source, but also if productivity, whether it's production or injection, is starting to decline, then this may give you an indication of where to target remediation and to clean up selectively to bring the well back online with the minimum interruption. So just finally, before we start to open up for questions and summarize the overall significance of this information, I just wanted to give an insight into some of the other steps that we're taking to improve this process further. So there was a logical extension from looking at perforations to looking at screens, but there's also quite a level in performance gain that we've got to achieve first. And if you consider a typical perforating gun, you're talking 4 to 6 shots per foot, and for a typical unconventional well we're looking at these days, 1,500 to 2,000 perforations isn't uncommon. And with the semi-automated process that we showed earlier on, by processing that with multiple analysts working in parallel, we can give information back to the customer on that in, sometimes a matter of days, more usually a week or so for initial results. But if we then scale that up to consider sand screens, well, we've got nearly a 20-fold increase in the density of holes and features that we need to analyze. And on top of that, there may be multiple screens inside the well. So we're now looking at potentially 100,000 or more holes to analyze. So the same technique of semi-automation is not really going to give us a result in any time frame that's going to be useful or beneficial to the customer at the end. So to tackle this challenge, whether it's increasing the speed of the perforation analysis or being able to break through and analyze the screens in a meaningful way, we've adopted machine learning techniques, and in particular, deep learning techniques, to try and bring this to a real-time or at least near-time deliverable. And I thought I'd show you just a little insight into the progress that we've made. Here we've got a little video clip of the model that we've set up working in situ. So in this, we've created an architecture that we can train and then retrain with additional data as we get it. We've broken up our data into specific classes, defining what it is that we want to look at, and what is a hole, and specifically what is not a hole. What are the things that we want to avoid? And we can then apply that to the algorithms, and they can start to learn that for themselves. We took a supervised learning approach to this, where we helped teach the system what we were looking for, as opposed to for an unsupervised approach, where we asked the software to look for the relationships for us. But the nice thing is about having that human interaction is that we're essentially checking the reliability of the results, and we can intervene and tweak the model as we choose. And just to give you an idea of the amount of data that we process here, a typical training exercise is somewhere in the magnitude of 400,000 images just to go through one iteration. So it's a very involved process. But the benefits are potentially huge. That firstly, we're now employing machines to do the work, and the parameters for picking the perforations or the base hole limits are now hardwired into the code, rather than being subject to human error and subjectivity that we may be able to deduce. But the other great thing is it also eliminates artifacts from the data set, that things like oil on the lens or contamination of the image, it doesn't behave in the same way as the background that we're looking at. And the computer has learned to differentiate between those two. Yeah, we've already mentioned about the removal of humans from the process, and the fact that gives us greater repeatability, which is a really positive step. But on top of this, the speed of response, that we're now not only fully automating the system, but we're able to capture the images and analyze them far quicker than we ever could in a manual sense. And to give you some indication of the level of performance that we've achieved in laboratory trials, we're seeing somewhere close to a 90% success rate in picking these perforations and base holes. And we're doing it at faster than real time. So we're actually running the video back quicker than we'd see it normally, which is a tremendous result. And the point to all of this is that the combination of this technique could lead to live real-time analysis at the well site, that we could be acquiring the data on intelligent coil or even E-line-enabled tractors and getting the results there and then in the field, which not only could help then for the next well or sequence of wells, but potentially with decision-making on the next stage and potentially avoiding some severe issues if they are observed. So again, there's a lot of performance gain that we might be able to take, and we're really excited about the application of these techniques. So just before we wrap up, really, I wanted to say again that there are a number of different applications covered within the main body of the paper that we haven't had time to look at today. A good number of these are also available on our website if you want to take a closer look at them. But the key thing that we wanted to stress is that the application of this visual analytics technique, combined with the new technology we use for acquiring data, really has transformed the way we view and use downhole video. Simply, the data density and the precision of the measurements we're able to take is far greater than any other technique available out there. So we're able to surpass the barriers that we had with other technologies and other logging tools. This in turn has led to a proliferation of different applications that we can now help, that previously there weren't solutions available to help diagnose and evaluate. And that, on top of it, has increased the demand for greater automation and image processing techniques. So we see this going forward as perhaps a software race, if that's the right way to put it, that we now have to get the computation to live up to the expectation and the performance of the hardware. But again, it's a very big step forward, and we can see from the customers we've worked with that this has been a significant improvement for the way they operate their wells and the way they plan their interventions. So with that, I'll wrap things up. And again, I really wanted to say thanks for your time and attention. I also wanted to draw your attention to the full SPE paper number, which I've placed on there. And again, if you do want to start a conversation about this, or perhaps look for additional information, then please do visit our website, because that has a lot of information there But if nothing else, on the very front page, you'll have your nearest EV sales representative on the home page, someone that you can reach out to and speak to. And all of our team are very experienced in their subject matter. So you will be speaking to an expert, and it really is worth making that call and having the conversation. But with that, I'll open up for any further questions. And again, thanks once more for your attention.
Hi, Tobben. So a few questions actually came in through the chat, but Glyn was proactive to reply to them there. One question came in from John Lassick, asking about whether we calculate the beveled entry area, and Glyn replied mentioning that we measure the exit hole on the pipe OD, and the beveled area is considered in the visual assessment we make for each perf, but isn't quantified. Was there anything else to add there, Glyn, or did that really cover it?
I know. I mean, hopefully that answered John. He seemed happy with the answer, but no, I can't think of anything else to add at this point to that question. The other question that came in was a little more challenging, asking about whether we could use the 2D images for kind of 3D stereoscopic images. So I did my best to answer that, although certainly don't feel as an expert to reply on that one. My understanding is, yes, you really need 2 images of the same feature, ideally at the same time, to be able to do that. And with the array camera, the images are we only get a little bit of overlap of the features in the wellbore, not most of the wellbore. So we can't really do that in a true sense of stereoscopic images at the moment. But perhaps when we look at future developments where additional cameras might be added to the array, that might be something that becomes possible in the future.
Yeah, that's right, Glyn. The way we designed the camera, we bring the light source with us and have it traveling along with the camera. And a stereoscopic system would really want to have 2 independent views with the same lighting parameters. So it's not something that we're able to do today. Although our research team, all based in-house, we've got a number of different projects looking forward. That's a terrible pun, apologies for that one. But a number of different technologies that we've got identified, and 3D imaging is certainly one of the areas that we're considering. But for what we've done to date with the capture of the 360 field of view and with the image processing that we've got for measurements, certainly in the circumferential and axial plane, a 2-dimensional measurement, let's say, I think that's been a terrific step forward. And combining that with other measurements, whether it's a multi-finger caliper, ultrasound, or a thickness tool, that can potentially give us some additional information, and is actually a very powerful thing to consider. But just back to the first question about the, if you like, the erosional cratering, if you like, I've just popped up an image here to explain that phenomenon, and you can see it here that this perforation on the left is what they look like if they're either brand new and virgin or unstimulated, and this is what happens over time with the proper treatment. We have the removal of the sharp burr on the inside of the pipe and a more smooth polished surface on that that piece of pipe. So again, visual assessment can be used to show that rounding, but also then the quantification of the exit hole at the outside of the pipe. So any other questions from the audience?
Yeah, we've got one that just came in from Jesse Stevenson. He's asking that he feels with wire wrap sand control inflow, the wire erosion would be significant prior to seeing a hole size increase, and can we see that?
Yeah, it's a great point, and it really depends on the screen construction, and this is something that I've looked at with multiple logging techniques, whether it's electromagnetic, ultrasound scanning, or more latterly with video. But this clip we've got here on the video wall is quite useful in that respect, because not only can you see the base hole in these conditions, but in a lot of cases you can also see the filter medium behind it. And for a simple wire wrap screen, yeah, you're right. The wire would probably give way before you've got the erosional effect on the base hole. But we may actually be able to see the presence, or more likely absence, of that wire wrap in the event that sand has broken through in that location. But just as a caveat to that, and again with a lot of testing that I did with operators, the erosional effect as the sand does jet through the base holes is phenomenally strong. And we did see quite a large number of perforations that were enlarged with sand ingress. And similarly, on the opposite side of the pipe, you tend to get a washout area as that sand impinged on the opposite face of the pipe. So there were a couple of telltales that we could look at. And I think, again, the video technique is a potentially very strong candidate for assessing the screen performance and condition. So Jesse, if you'd like to take up that discussion further, I'd be very happy to talk through some of my experiences and listen to potentially the issues that you're having. I can see Jesse's nodding. Yeah. Okay. Any other questions from the chat channel, Mike?
Yes, I have a question here from Argentina. I remember spending some hours looking for any kind of collapse or restriction in fracture wells. So I'd like to know if there's any automatic mode to find small restrictions or collapse, because the ones you show here in the pictures are very clear, but sometimes you don't realize very easily when you look to the video. So if there's any kind of automatic way to find these small collapses. Thank you.
No, that's a great question, and again, an area that we thought about quite a lot is essentially collision avoidance, or let's say defect detection. It's not something that we have the ability on the video standalone today, but what I can offer, and again, this is sort of real world solutions here. We have a technology that we refer to as integrated video caliper, and that is the combination of downhole video and multi-finger caliper into the same BHA, and I'll just show how we use that in this video clip. So we have a side view camera, down view camera, combined with multi-finger systems, and what we can use that for is to map the three-dimensional shape of the well as a logging pass, and with an analysis sequence that we've developed, a process that we call pipe deformation analysis, and more critically drift analysis techniques, we can recreate the true three-dimensional geometry of that well, and we can then simulate the passage of your BHA or planned BHA through any anomaly or restriction that we find. And what you get at the end of this process is a nice chart that plots the size of your BHA against the limits of access. So in this case, we're saying for a given diameter, you can say, this is my BHA OD. You can then look up the maximum length that will fit through that restriction. Or you can drive it the other way and say, this is my maximum rig up height. what's the largest diameter that will fit through the anomaly. And this is something that we see a lot of in unconventional wells with the phenomenon of frac kits or well-to-well interaction. We do a lot of diagnostics on this, and in some cases, and this example in particular, this can happen very early on in the well's life, even during the plug and perf operation. And we can then help understand the severity of that. And in this example, we were able to offer a revised BHA that would fit through, get the job done, and ultimately bring the well back online. So although it's not a straight video solution, that combination of caliper with video in the same run is something we do very, very regularly and has a very powerful effect, especially for looking for deformation and limits of access.
Okay, thank you.
And I should actually note that the next webinar that we'll be running in, I think it's 2 weeks' time. Is that right, Mike?
Yeah, that's right, Tobben.
Yeah, that will include more case studies based on that technique from a mixture of producing wells and actually well abandonment case studies that we've looked at and employed the same technique.
We've got another question here in the chat from Larry. Larry's asking, roughly what percentage of fluid-filled wellbores do you get inadequate visual clarity with the OPTIS Infinity in comparison with previous EV systems?
That's a very good question. It's an interesting point that you raise, and I'm just going to pop right the way back to one of the earlier video clips that we had in the sequence. Compared to a conventional downward viewing camera, because we're actually looking sideways at the pipe wall, we're looking at a far reduced field of vision. So the amount of contamination and particulates that may get in our way is very limited. And in fact, in this video example here, you can see that there is actually quite a lot of loose material and debris floating inside the well. But because that moves and behaves in a different way to the objects at the pipe surface, it's quite common that when we do the image mosaicing, as we call it, those loose particles actually are eradicated from the final image. So there's a twofold system there, that firstly, we're less sensitive to contamination because we're not seeing or trying to look as far through the fluid, but also with the post-processing, we're actually able to eliminate some of those unwanted features and get to the main event. Can I put a number on that? I'm not 100% confident I can today, but in fact, just before we came online here today, we were having an operations review, and we were analyzing the data for the last 12 months of our operations. And we found that in 92% of the wells that we go into, we're able to overcome any sort of well contamination issues and get very clear images. There are very few wells that we struggle with. And in most cases, if we have, we'll come back with a revised well cleanup procedure and typically get it right the next time. So it's not something that we're massively hampered by, one or two exceptions, of course, but we have found that the Infinity system is less sensitive to that type of pressure, but it wasn't a huge problem for us in most cases. So Larry, I hope that answered your question, and also I hope that wasn't a hint that you've had a few false starts in the past. But if you want to talk anything through, then again let's talk, and potentially we'll come up with a solution for the system that you have. So I think before we round off then and start looking at the results of the poll, just to extend that conversation, we are always asked about our ability to operate in difficult well environments, and how exactly we go about planning and executing the jobs. So I thought it would be worth just running through a couple of quick slides to actually give a bit more detail on what it is that we do and what can affect the performance of the video systems. And it's no secret, the images that we've shown you, we've chosen from some of our best operations, but again, they are real well environments that we've been into. And the reason that we're so successful is mainly with the fact that we provide a service. We don't just pack you off with the user manual and the technology and wish you luck. There's a lot more to it than that. That we have the experience in conditioning the wells and manipulating them to get them to the way we want. And a job will usually start with one of our field operatives or our technical sales team working with the operator to look at what the starting point of that well is, what fluids it may have inside it, and then what options we may have to manipulate those if there are difficulties in seeing through them. And those difficulties are normally down to two main factors. Pigmentation of the well fluids, as we're showing here on the left. We've got some nice clear mineral water compared to a soda here, some cola, and they have roughly the same level of particulates in them, but the cola has a pigment to it which absorbs the light and prevents us from creating an image of the coins at the bottom of the glass. The second parameter is suspended solids, and in this case, what we call the NTU scale here, increasing particulates suspended in the liquids themselves. And for offshore operators, this is where filtration comes in and typically inhibited seawater, but also on land trying to get potable water. That can be a challenge in remote locations. But again, we'll take a look at what is likely to be in the well. We'll look at the access to circulating the well. It could be that even shutting it in, if there's free gas or produced water, we might be able to position that column so that we've got the clear medium in the place we're interested in recording. So again, a lot of work goes into the preparation, and usually if you do the homework up front, then when you come to do the job, it's relatively straightforward and successful. And with the type of work we've been doing in North America on hydraulic fracturing and assessment of perforations, we've got some very, very good cleanup procedures that actually we've in some cases cleaned up the well way beyond what we needed to do. And then we've learned to relax the cleanup to get to a happy medium where we're not spending too much time and cost, but we're also getting the images of the quality. So I'll give again just a very quick illustration that the presence of oil in the well is not necessarily a terminal thing, that we use special coatings, surfactants that we place over the lens of the camera, and this can actually repel oil from the surface of the camera as we move through it. So in this video clip, we're in a highly deviated well that's undulating as we go along the reservoir section. And as we come out of the produced water through the oil and into the free gas, the image on the camera instantly clears up and we can see again. And when we go back the other way, we'll go through the oil into the produced water again. And again, we'll get back to clean images almost immediately. So we can certainly get through a column of oil into a liquid phase and get images there. And we're not necessarily hampered by the presence of oil. It's just one of the variables that we've got to manage with the well operation. Okay, Mike, should we just have one final round of questions and then we'll have a look and see if we've got any more results from the poll that we send out.
Yep, nothing's come through on the chat there, so I think we're good to go.
Okay, let's take a quick look at that then. Let's find the right window. So here we go. So let's just update that. Okay. So for those of you that haven't far run through the questionnaire, there aren't many questions, so it won't take more than 5 minutes. But a quick snapshot of those that did respond. We can have a look at the results here live as they come in. So there we are. That's started to populate now. And our first question was placing the challenges that we presented in the order that they affect your business. And just looking through this so far, yeah, there we go. So the largest number of hits is the number one priority, appears to be corrosion and life of well extension. So particularly in maturing assets and locations, that's no surprise. Keeping these wells going for longer, especially when drilling is a challenging environment, I think that's understood. Yeah. But a number of people saying that perforations and reservoir contact is an issue, and a few here isolating the source of water. Yeah. Then looking at how many of your wells are affected by this, for those that responded, the top 2 hits are between 25 to 50%, and in some cases greater than 50%. So some quite widespread issues there. The most difficult part of overcoming the challenge, well, that appears to be locating the issue and identifying the root cause. So I guess there's plenty of scope there for some diagnostic and evaluative services, helping to steer the process from there. And it looks like we've got a fair number of seasoned camera users here, a number of people using it for emergency situations, blockages, things stuck in the well. Some newbies that haven't tried it yet, so we'd love to change that. And in fact, some people here are also using it as a diagnostic tool ahead of the operation and planning their next move based on that information. That's great to see. And not a surprise, given it's relatively new, we've got a number of people saying that they haven't used the quantified vision yet. But also encouragingly, some of you have got back and said, yep, that's something that you've used. So that's really good. Thanks for filling that out and giving us that information. That's really interesting to see. It's also great to see that we've had some people give feedback on the content that we've presented today. So if nothing else, if you wanted just to log in, follow the link, and give us some feedback on how we did today, that would be terrific. Yep. Well, thanks very much for the information there. So with that, I'll hand back to you, Mike, if you want to wrap up, and we'll say thanks once more.
Yeah, I'd like to express my thanks to everyone who joined in today. I really hope you enjoyed the content, the format. You know, with most of you all working from home, we figured this would be a good platform to connect and share knowledge on these topics. So just to wrap up, as we mentioned, our next webinar will be in about 2 weeks' time. Many of you have already expressed interest in it through the sign-up form on our website. If you haven't, you can head over to our website and visit our technical webinars page. So the topic of the next webinar is, it's actually a rerun of a presentation that we did at the SPE Asia Pacific Wells Week back in 2019 in Malaysia. So it involves case studies from the North Sea, from US land, and really it looks at 3D modeling, pipe deformation. We mentioned earlier that we have this pipe deformation analysis service. It looks at you know, helical buckling and drift simulations to kind of improve the efficiency of well interventions. So hopefully you can join us for that in 2 weeks' time. And once again, thanks again for your time today. And yeah, we'll hopefully speak to you guys soon. Thank you.